So without further ado, I'll hand it over to Ron VK3AAN. Now, this is a very interesting and topical subject because many of us are getting out there activating summits, parks on the air, silos on the air, everything else you can activate on the air. And it's also very important for emergency communications. All these antennas that we're constructing for field work, long wire antennas, half wave antennas, dipoles, etc. We also need to know about balance when we're constructing these antennas. So it's a really topical subject. So without further ado, we're lucky to have Ron here and his knowledge on Baluns and RF Transformers. So thanks, Ron. We'll pass it over to you.
Terrific. You want me to use that, do you? All right. I was going to start out, anybody that's not interested in the topic is most welcome to take have a cup of coffee or whatever. I don't believe in locking people down to getting involved in something they're not particularly interested in. But given how cold it is tonight, I've obviously got a hardcore company, so if you wish to go and have a cup of coffee, yes, okay. This isn't a lecture, it's a discussion, and therefore I want everybody involved. Please speak up, and please try and stay on topic. In other words, I'll go through systematically what I wish to cover, and if you've got any questions or appropriate comments that don't need to be censored, then you can make them, and I'd appreciate them. At the end, we'll have a bit of a talk and give everybody anything that you've sort of forgotten or missed. I'll give you a chance to pick up on them later on. So, all right. I think most of you can read. So the aim of the project is to get people, or amateurs in particular, to be conversant with transformers. Now, from my experience, I've found that the training that you get in electronics sidesteps transformers. Like I was at TAFE for a short while, and even there was very little coverage of transformers. Now, I was fortunate in my early days that I was in a location, Trimex Transformers. I don't think they'll mind me giving them a plug. I doubt whether they're still in business actually, but they actually made a range of transformers for the telecommunications industry. So, all right, any queries at this stage, or we carry on? First, I'd like to just discuss some of the applications of transformers and where they fit into electronics. Now, it's starting to happen that transformers are pretty unique to every application that they're in, and therefore are expensive. You can't just go down the street and buy a transformer for a specific application. So therefore, it's very important that as a technician or working with transformers, that you have an understanding of what's involved with the transformers. The uses of transformers. Come on, people, uses of transformers. What are they used for?
Changing DC voltage, for that matter, sorry, AC voltage.
Yep, all right. So how do they do that? They chop up the DC, make an AC signal, and then put it through the transformer. All right, good. Any others?
Impedance matching.
Impedance matching, yes, important.
Balance to unbalanced lines.
Yep. Yeah, carry on, you're doing well.
Step up, step down.
Sorry?
Step up and step down.
Yep, voltage change or...
Ratio.
yeah, what about in instrumentation and that? Yeah, isolation, safety, current transformers to stop or to measure current in lines. In other words, just a variation on the use of transformers. Now, all right, that's sort of got your thinking a little bit, and that's the aim of the project, is to try and get you thinking. Types of transformers. What sort of transformers can you see? We had a bit of a, with the switching for power. Now that's, I'm sort of alluding to the, where their applications are. There's ferrite transformers, there's silicon steel transformers, and there's mu metal. They're just as a starter. Now, each of these types of transformers has its own application or area where it excels at. A lot of it's to do with price and the actual engineering required. We'll do the one that's least used nowadays first, and that's mu metal. Mu metal has a very high permeability. In other words, for a few turns of wire, it'll generate a very high flux density. In other words, it's low reluctance to the establishment of flux. These are terms associated with magnetism. It's because of the high flux density, but the other thing is it won't go up to high frequency. It'll do a hell of a lot better than silicon steel, but you're lucky to get much more than about 20 kilohertz. So typical applications are for audio transformers, which nowadays are hardly used. So mu metal is hardly used. It's very expensive. It requires annealing, etc. One of the other uses for mu metal is for shielding, because it's very low reluctance. In other words, it establishes a magnetic circuit very well. If you put it around, say, and this is another old technology, is cathode ray tubes, which was one of the areas where they used to be used a lot, mu metal. The cathode ray tube works on electrostatic and magnetic fields to shift the beam. Now, if there's an external magnetic field near the tube, if it hasn't got a mu metal shield around it, the beam will blur and upset the actual beam itself. So that's just to give you a general idea of mu metal. And typically, they'll take flux densities up to about 12 kilogauss. So that's pretty high. Considering power transformers, you're looking at about 7 kilogauss. So that means you can put twice the amount of flux. How do I get that back? Without, shifting the mouse. Yep, good on you. I didn't switch it off, so. Where am I now? Can I go backwards?
Back arrow. Here we go.
Good on you. All right. Thank you. So silicon steel transformers, power transformers, are lucky to go over about 100 hertz in operation, about 6 kilogauss. Now, the thing is that we'll look at the effects of flux, or the amount of flux you can generate on the actual operation of the transformer. The idea is not to go into it to a high degree, but to just go through it so you understand the interaction between the number of turns, the type of material, the cross-sectional area, the size of the transformer, etc. And ferrites. Now, ferrites work up to about 4 kilogauss. So that's significantly lower in flux density. That means to get the same output, you've got to put more turns on. Or and we'll look at this, as I said, later on, you use them at higher frequency. Now, the advantage of ferrite is that they'll go up to 30 meg or more. Not a lot. So in other words, up into the HF band without too much panic. When you start to go VHF, then you start to look at air core, and we can quickly look at that as to why that's the case. But the thing is that at those frequencies, you don't need a high permeability transformers. And actually, the problem is with ferrites, especially what's available through the local stores, is that most of the ferrites are made for noise suppression, and that was one thing Chokes Transformers didn't come up with, and for power supplies, switching regulated power supplies, etc. The use of ferrites for radio applications, amateurs don't build too much with ferrites. Most electronics people don't use ferrites, so the stores don't stock them. So if you want ferrites, you've virtually got to go to off the internet, these suppliers off the internet, TDK or somebody like that. There's a whole range. We've looked at sort of materials, basically, the shapes involved. Anybody like to come up with some of the configurations that are used in transformers? No. Yeah, that's typically where are they used, E&I. Power transformers, yep. Then ferrites, typically where are they used? Yeah, what about just general communications? All right, any more? Phil, you agree?
Just toroids, round toroidal transformers.
Sorry, what transformers?
Oh, you're asking for comment about different shapes.
Yeah.
Or toroids.
Yeah, toroids, yes, very much. Typical use, yeah. Where's the toroids used? Where are the toroids used? Yeah, in mainly radio, actually. And part of the problem with toroids is that the winding of them is a bit expensive. Most E&I, pot cores, etc., have a former, a plastic former usually, and what happens is you can wind that on a machine separate from the actual core itself, and then just plug the whole lot together later on. Whereas with toroids, you've got to use a spool, and you clip that through the centre of the toroid, you run the wire onto the spool or former, and then it does a bit of a jig. You tie the end down, and then it sort of dances around and puts the wire that was on the spool onto the actual toroid. So, but that is time-consuming and expensive. Sorry about that. Any others? Any other thoughts? I've seen mu metal transformer, a mu metal transformer used up to 5 megahertz. Now, I previously said 20 kilohertz, but they will actually run in the earlier days of TV and that, where they wanted to, provide unbalanced to balanced, etc., matching that, or impedance matching, that they've gone to the trouble of making mu metal transformers, and that must be a very expensive exercise.
The tuning slugs go up and down as well.
Yeah, in IF cans and that. The communications industry also uses things like cross-core transformers, etc. So there's a whole range, and all these transformers are all designed to provide a low reluctance magnetic path for the flux. That's the whole aim of the project, is to establish a magnetic field efficiently. Now, how do we make up a balun? Or this is just a brief outline to say that you'll know what sort of I'm sneaking up on. And the first thing is to select a suitable material. Now, we've already discussed materials to some degree, and the suitable material, as Colin's showing, is probably ferrite. And one of the things to do with ferrite, the ferrites used for power supplies, etc., the whole idea is to have the permeability as high as possible. In other words, given the amount of signal or number of turns, you get the most flux. With radio circuits, if you put on too many turns, you pick up a whole lot of problems. So the idea is to keep the number of turns within a workable range. It's no good having one turn because you can't set ratios and things like that. But it's no good having 100 turns because the capacity between the turns themselves becomes part of the actual circuit. So the idea is to get a suitable balance that'll actually do the job. Once you've selected an appropriate material, which is usually pretty low permeability, something like about 20 is probably a pretty good figure. The permeability of a vacuum is 1, so it's 20 times better than a vacuum. So, but given that if you go onto VHF, UHF, you don't need a core because you end up with too much inductance. So the idea, we're talking reasonably specifically for HF, the HF band. The first thing to do is once you've got a core that'll do the job, and we'll look at a couple of practical applications a bit later on, once you've got a core that'll do the job, is to just wind a test coil. Now, it's not easy to get data sheets from suppliers, especially as amateurs. You can go to a shop and buy cores that sell RF equipment, but to get the appropriate data sheets, and then also to understand them, because there's two, or there used to be, I don't know about now, but you had the two systems when you start talking about Weber and Gauss and etc., Maxwell's and all the Orsteds and all the different parameters associated with transformers. You're talking about the British English based system and the European system. So the whole idea of this is to circumvent that need to go to data sheets which could be reasonably complex. I know when I first saw a data sheet, I was very fortunate because the supplier that wanted to sell us the ferrites gave us a small booklet on how to apply their ferrites to the actual application. So you took the information off the data sheet, plugged it into the formulas, and came out with the appropriate answers. So, in other words, you wind a test coil, and from that, you determine the actual inductance, and from that, you can then scale that back to the inductance for one turn, which is called AL. It's the actual then you've got to look at your design, what you're doing with the transformer or balun, if you like, as to what it's driving. Is it driving a dipole or an end-fed antenna, which we had a bit of discussion on a couple of weeks ago. In other words, what impedance ratio you want, whether it's 50 ohms to 200 ohms or what. Once you know the actual impedance, you can then calculate the number of turns from a very simple rule of thumb. You wind a prototype and see if what you worked out is going to work, and then you evaluate whether the transformer's any good or not. So that's the basic procedure. Any queries? How are we going? Now, we were alluding to some of the problems with transformers. There's the transformer has a couple of windings, usually a transformer or an inductor, it doesn't matter which. And the copper wire itself has resistance. That's R1 in this case. We'll put it as R1 and R2, I think it is. Yeah, R2, the winding resistance. Also, depending on the type of core, you get a certain amount of leakage inductance. Now that is a major flaw in transformer design. If you use E and I cores, they overlap each other, but the flux has to go through that gap, or they're not a really good join. One of the things they use in power transformers, and we got to mention, was C cores. They actually use layers of metal to make up a C shape. Then they cut it in half, polish the surfaces, and then put the two halves together around the bobbin. So very effective, very quick, very effective. And they just use a banding machine to lock the core in place. So the whole idea is to make sure that this leakage inductance is minimal, which is leakage inductance X1 and X2. Then one of the things that I saw in one of the amateur radio magazines is that a really neat trick was to get a couple of centimetres of jumper wire. Now, if you're an old telephone technician, you know what jumper wire is. It's just hookup wire. You twist it for 1 or 2 centimetres, and that's 30 picofarad. You can use that in a application within a radio. When radios were pretty rough, that used to be a possibility, a way of getting a quick capacitor, and they're tunable too, quite easily tuned. So imagine in a transformer where you've got 100, 200 turns, and they're all running parallel to each other. What sort of capacity are you looking at? Now, we'll look at a reactance chart later on, and you'll see that depending on the amount of capacity, that can actually be a problem. So as I said earlier, the whole idea is to keep the number of turns down to a manageable quantity, because if you put too many turns on, what happens is you start increasing the capacity within the winding itself. Now, another problem is the capacity between the windings. What do we call that? C mutual, the mutual capacity. When you go from unbalanced to balanced, and you put one winding on top of the other, you layer wind the winding, the unbalanced end will reflect through to the secondary, and it will unbalance your secondary too. So one of the things that they do is they put a very thin copper shim around, they wind the primary, and then just put a copper shim around the primary. And as long as you don't short circuit make a short circuit loop, you put a bit of insulation between. And I must admit, the first one I made, an engineer wanted me to make what they call a screw balun. And I made up this balun, and yeah, I put the shield in between the primary and the secondary, and gave it to him, and he's scratching his head and wondering why it didn't work. And of course, I didn't know about insulating the overlap on the shield. And of course, there was a short-circuited turn, and it worked very well, actually. It was driving all the energy into the shield. But the thing is that most of the radio transformers are on toroids. You can use bot cores, etc., but most transformers are on toroids, and it's very hard to use a flat piece of shim, wrap it around and make a shield. So you've got to use a bit of ingenuity to overcome that problem or else you don't worry about whether it reflects or not. That's the other way of looking at it. Radio sets are pretty tolerant as far as SWR, etc. goes. In say a carrier telephone situation, they'd have a heart attack at what actually happens with a radio set into a transmission line. With carrier telephone systems, they wouldn't accept that in the slightest. That's just totally unheard of. And even the unbalance from primary to secondary is a major thing. So, all right, we've got the resistance losses. When you've only got 20 turns or something like that, as long as you've got the wire sufficiently heavy enough to carry the current, it's not a problem. The resistance is definitely not a problem. Leakage inductance, you're using a toroid, there's no gaps in the magnetic circuit, so therefore it still can be a problem, but in generally it's not. There is as I said, I worked at Trimax, and they made transformers for the Ikara missile. And they were what they call a square loop material in the transformer, and they used positive feedback off the winding to drive the transistors so that they switched as a switching regulator. And they were making these up and selling them no difficulty at all. But then what happened is they got a reorder for the product, and so they, I think it might have been Fairchild, I'm not sure, but they reordered a couple of more trays of transistors, probably 200 or 300 transistors for these power supplies, and they put them in the actual power supply, and the power supply wouldn't work. It was drawing current, but it was just getting hot. And they found out that what it was doing was running at a higher frequency, a much higher frequency. And what it was due to these stray capacities and leakage inductance. In other words, the basic rule is try not to put a feedback circuit around a transformer, because the leakage inductance capacitance isn't always that predictable. If it's tuned, it's probably, you might get away with it, but if it's a wideband transformer, you'll probably find that you might get a lesson on how to wind transformers. Any queries? How are we going? Yeah.
Someone online has asked, what's the difference between a balun and an unun?
A balun and a...
Unun.
I haven't heard of.
Unbalanced or unbalanced?
Oh, balanced and unbalanced.
Unbalanced to unbalanced, I think is the question. Yeah, balun and an unun, I think the person on the so.
I'm sorry, I still can't see a question in it.
We just asked, what was the difference?
Well, a balanced transformer, let's put it this way, your coaxial cable is unbalanced. In other words, it's got earth on one side. Now, with transmission lines in particular, if you don't want noise getting into the line, then if both wires are balanced, then what happens is any radiation through the air won't be effective in just one wire. In other words, you'll get a sum signal. What happens is if the pickup signal through the air is into both wires, and because both wires, one's sort of positive, one's negative, and the relationship of the pickup signal opposes each other and they tend to cancel out. Now, there is another trick. They swap the wire, they do a crossover in the wires at given intervals to make sure that this balance remains good. But an unbalanced circuit is very susceptible to noise and pickup signal. So the main difference, the physical difference, is actually in the winding, the way you actually go about winding the transformer, and whether you use a shield or not between the primary and the secondary. If it's highly important that it's balanced, in other words, say a communication circuit, then you start using shields between the primary and the secondary, things like that. Oh, sorry, Ron. I should have switched that off. All right, any other queries or how are we going?
Can I make a comment about the air gap and the magnetic effect on the steel? A 1 thou air gap in a magnetic circuit is equivalent to 30 inches of mu metal. So if you had the energy required to get across the gap is that length in steel. So that's why the continuity of the magnetic circuit is so important. But that's the relationship, about 1,000 inches, 30 inches.
Yeah, that's an interesting observation. And a lot of these practicalities and understanding of transformers just comes from being there doing it. It can be, from an outsider looking in, it can look very hard. But as I said, there's a few rules of thumb that make it it's quite simple. Now, one of the characteristics of metal being magnetised is hysteresis. And the thing is that you can have the switching regulated power supply I was talking about that's free running. They use a square loop material. In other words, the width of the return line, the separation is quite a distance. In other words, it takes a lot of magnetism to change the field back in the opposite direction. You've got to use a lot of force. The other thing that this diagram shows is the curving at the top of the actual, what would you call it, a trace or whatever. That's saturation. In other words, you've got your magnetising force and your flux density. Now, as the magnet, it's not linear, it's linear to a certain degree, but once you get up to the limitations of the actual magnetic material, it actually saturates. Now that, for ferrite, we said was about 4 kilogauss. So that's worth remembering. It's very important, especially when you're trying to work out what power rating the actual transformer will carry. That's quite important. And also the number of turns. Now, the Holy Grail. It's interesting, this one, because that E equals 4K NF phi. 4K is basically the waveform. Now, a square wave, if you're putting a square wave through your transformer, I think K is 1. Anybody got experience with form factor? Oh, I can say anything. No, I'm pretty sure it's 1. A sine wave, I think, is 0.637, and a triangular waveform is 0.5. But for our application, this formula, we don't need it. I've put it up for a very specific reason, and the reason is that you understand the relationship between the different parts of the transformer. N is the number of turns, and that's where we come in. The frequency, in other words, what bands you're working over, and phi is the total flux. Now, that total flux is important because if you push it too hard, you can saturate the core, and then once you start flat topping the sine wave, my guess is you'll get high levels of third harmonic out. So any queries on that just at this stage? I'll refer back to it later on because it's a very important relationship. The interesting thing is I worked on a power supply, and using this formula, we've worked out the actual transformer. It was a switching regulated power supply, very similar to the type of thing that they use now, but it was in the early stages. It was only running at 20 kilohertz. And we never, ever worked out the inductance on the windings. There was no need to, because we knew what the frequency was. With the square wave, you've got to allow up to about the 10th harmonic, because if you don't do that, so that means that if you've got 20 kilohertz, you've got to allow for the transformer to carry 200 kilohertz without any worries. Because if you don't have those odd harmonics in the waveform, then the efficiency of the transformer goes down considerably, just dies. So phi, as I said, that was off the manufacturer's data sheets, and using the frequency and the flux density, we knew the waveform, and so therefore we could calculate the number of turns necessary so that the transformer wouldn't saturate. We knew that we could go up to about 3.8 kilohertz, I think, kilogauss, I think it was, before we pushed into the area of saturation.
Sorry, I don't understand the waveform. The K is some sort of constant.
Yeah, that's the
4 is multiplication. So with the particular waveform, it's 4 times K.
Yep.
You said another waveform, it's point something K.
yeah. Now,
It's just the way
K,
it is. K is the constant.
K is a constant for any particular type of waveform.
Yep.
Now, for a square wave, I believe it's 1.
1K. Yep.
For a sine wave, it's 0.637.
Yep.
And for a triangular waveform, it's 0.5. Yeah, all right, how's that? Do you understand? But the thing is, for our application, because we're working over such multiple bands, and it's not necessary to, that amount of error isn't significant. It's not a problem in the slightest. Now, when you put a winding, the top part of the diagram, when you put a winding where AL equals 1, that's the inductance for 1 turn. Now, that's, some of the manufacturers actually give that value, and it's very handy. But for us, what we're really trying to do is determine for the ferrite what the AL is. We're trying to work out what it is. Now, the second diagram shows AL equals 1S plus 1M plus 2S plus 2M. In other words, the circle on the left, which is the end of a piece of wire, obviously, or not obviously, but that generates flux, that wire number 1, which gives you self-induction, but also the flux cuts number 2 wire. So you get the mutual induction into wire 2. So in other words, you get the inductance from the self-induction plus the mutual induction, and then wire 2 does the reciprocal back to the other wire. So in other words, you get the self-induction in wire 2 plus the mutual induction back into wire 1. Yeah, anyway. And therefore, if you double the number of turns, how much inductance do you end up with? What happens to the inductance? The square of what? The square of the number of turns. Yeah, you're right, Colin. You just so in other words, that relationship is very important. That depending on how many turns you put on, the inductance goes up as a square ratio. And there's the formula, very complicated, L equals n squared AL. Another really basic formula, which is quite important for our application. The previous formula wasn't, we're not going to work with it much, but this one, it's important that you understand that relationship, because in the long run, the whole idea is to work out the number of turns that you're going to put on this transformer. And the way of doing it is to put a test winding on, measure the inductance. Once you've got the inductance for your test winding, then you scale that back to 1 turn, and that's your AL value. So you've virtually worked out what the manufacturer might tell you, maybe not. And then from that, you can then scale it back up the other way to the inductance you require. Now, we'll look at how to evaluate that inductance shortly. There's the test setup for measuring the actual inductance. That's one method. There's several methods of doing that. You might be interested in looking at that. That's just that's what you've on the screen. And one way of measuring inductance, of course, and Phil won't mind me giving him a plug. I've already checked with him. I've got him to sign a form, copyright form, so that this is a version of his LC meter, and it's quite good at measuring inductance, although the one I built has got a minor problem. I think you might see that the switch is in the C position and it's measuring inductance. So a minor technicality in the layout. I've made a mistake. Another way of doing it, there's the inductance meter. You might want to have a quick look at that. As I said, that's just a version of Phil's design. The back comes off this, so I was going to put a rubber band around it, but I forgot. So that's my version of I suppose you'd call it a network analyzer or whatever, but I like to call it a HF scanner because the whole thing that it does, it scans a range of frequencies. There's the coil that I've handed around, and as you can see on the graph, that it's got a resonance, a peak, at about 2.628, I think it is, megahertz. So in other words, all it's done is saved having to use an oscillator and a crow or a voltmeter and slowly work it across the band until you find that actual resonance, that peak. So the whole idea is to work out the resonant frequency. And if you know the value of the capacitor, then using formulas or a reactance chart, you can then work out what the inductance is. So the whole idea of what we're doing now is to work out the inductance of our test winding. So this is doing it the hard way, using a signal generator, the tune circuit C and L. What happens when a tune circuit resonates? What's the significant thing about it? Sorry? Yeah, all right, but there's another way of putting that, or a better way. In this application, why have we got R? Sorry, high impedance. Yeah, it goes high impedance. So that what will happen is while you're off frequency, below the resonance, L will shunt the signal and you'll get a low signal on the meter. As you approach resonance, L and C cancel out, and therefore the impedance of the tuned circuit will be high compared with R, so therefore the signal will go up, and then as soon as you go out the other side, the high above the resonance, the capacitor shunts the signal and the signal on the oscilloscope or the meter drops away. Now, once you've worked out the resonance, you can use the reactance chart, and along the bottom is the frequency. So in other words, that's your frequency of resonance. And if you use a capacitor that you actually selected beforehand, and I'd suggest a pretty typical value that I've found is 100 picofarad, and you'll find that what I'm handing around had a 100 picofarad capacitor on it. If you look at the actual chart, you'll find that there's a line for 100 picofarad there somewhere. And from that, you can work out where the resonance, you've got the resonance, you've got the actual capacity, therefore you can work out the amount of inductance that's required. Now, the other way to do it is to go back to the old formulas, FR equals 1 over 2 pi root LC, and do some calculations. But those resonance charts are in the amateur radio books, and you probably get one off the internet without too much difficulty at all. Any queries? How are we going? It's all a bit too simple. Now, this is one of those rules of thumb. If the inductive component equals the resistive component, then the phase angle is 45 degrees. That means that the inductive component's 90 degrees out of phase with the flow through the resistor. So the overall impedance, 1 over RJ, 1 on R1 over RZ or something or other, isn't it? But the thing is, it's 0.7 of the two in parallel, the inductance and the resistance in parallel. So, and at 45 degrees, you end up with a SWR on your, even if you're 100% matched, 45 degrees, you'll end up with an SWR of 1.5 to 1, or slightly less actually. And the danger of that is that with that SWR, when it comes to tuning your aerial, you're going to tune the aerial to suit the transformer, not to suit the best radiation signal. So the idea is to try and keep that SWR down. Now, if the inductance, in other words, the inductance of the transformer, the secondary, is 5 to 10 times the actual load impedance, then that phase angle becomes negligible. For radio purposes, it is negligible. It's not a big problem. Now, the idea is not to go 100 times, because if you make the reactance 100 times, what happens?
So saturate.
Sorry?
Saturate.
No, actually it's the other way around. But that's good. Thanks for trying. Anybody else? We talked about it, one of the major faults of the radio transformers. Capacitance. You're putting in more wire, the wires are running together. So the idea is to try and keep this, the inductive value of the transformer as low as you can in keeping with your application. So what end of the band would you work out what reactance you want here? Is it up at the high end or the low end?
It's only going to get better if you start high and work down. Is that right?
It's,
High is going to be worst case scenario.
no, it's the other way around, sorry.
Jeez, I'll get the right ones.
E equals 4K NF phi. N is the number of turns, F is the frequency. So what happens is if you go lower in frequency, the number of turns remains the same, the magnetic circuit remains the same. So what happens to the flux density?
Try again, it gets less because there's less.
It's got to go up. To balance the equation, E equals 4K NF phi, if the frequency goes down, the flux density goes up. And that's why, with switching regulated power supplies, they're such small transformers. Because instead of running at 50 hertz, they're running at 50 kilohertz. And therefore, you don't saturate the transformer. You can put a lot less turns on and make a much smaller transformer. You're not going to saturate for the given cross-sectional area. So that's, and ferrites fit into that well because they'll take the frequency. There's 50 kilohertz, and for a square wave you allow 10 times at least, but 10 times is probably a good figure. 10 times the frequency, that's 500 kilohertz, and they'll go up to 30 megahertz, no problem at all. So it all gets down to your transistors, how fast your transistors will go in the power supply, as to whether they get hot trying to switch the power on and off at 50,000 times a second, especially when it's a 5 kilowatt power supply or something like that. Any queries? How are we going? Yeah, no, please. Look, honestly, it's not, the idea is to try and get you thinking. The idea is to sorry?
That holds true. The lower the frequency, the more inductance you need for that transformer.
Correct.
Yeah. The same with power or audio. If it hasn't got enough inductance, your low frequencies won't come through. That's right, because you haven't got enough in self-inductance or whatever.
Because the reactance, the inductive reactance, shunts across the load. Your phase angle starts to come into play. You end up, 45 degrees or even worse, the whole load becomes reactive. So the whole idea is to keep that reactance up, and the higher the frequency, that reactance goes up.
Yeah.
Now, if you want to work out the number of turns, just wind a test coil. So you get your ferrite. Now, I'd suggest something like 16 turns. Why is that? Because it's a nice binary number. You can divide it by 2. And as we said, the AL, or the inductance is n squared times AL. So in other words, you halve the number of turns and you go down 4 times down in the inductance. So a couple of seconds of mental arithmetic and you've got the figure. So in other words, I've given an example there. For 16 turns, let's say it was 40 millihenries, which is probably, might be a little bit low for most applications. Therefore, if you halve the 16 turns, you get 1/4 of it, which is 10, etc. Any queries? How's that going? So pretty simple, isn't it? And as I said, it's simple rule of thumb. And now once you've got AL, which in this example is 0.15 millihenry or 150 microhenries if you like, you can then apply that to calculating your winding, this winding here. Hold on, we're missing something somewhere. I don't know what happened there. Excuse me. Quick revision. LC meter. Yep. Reactance chart. Oh no, sorry. We're starting to hit the final result. One thing that I missed out on, and I've put it up, started to do it on the board, is the Z ratio and as relation to the turns ratio. Now, for most technicians or people in the industry, they'll know that straight away. In other words, if we've got a 50 ohm transmitter and we want to go into let's say, a load with a 2-to-1 turns ratio on it, what's the actual impedance of the load for a 1-to-1 SWR? What's the relationship? Yeah, that's right. It's the square of the turns ratio.
The impedance ratio is square of the turns ratio.
Correct.
Old amateur taught me that. He said that's one of the most important things.
Yeah, that's right. And it's very important in this application too, because you've got to work out your transmitter's 50 ohms. If you want to go into a Yagi, which is 73 ohms, then you've got to work out a turns ratio that will actually allow 100% transfer. Now, the reason why, just quickly explain it, the reason why that's 200 ohms if we've got a 2-to-1 turns ratio, in other words, there's twice as many turns there, P equals I squared R, which is 1 amp at 50 ohms is 50 watts. Therefore, it's 50 volts. So you're putting through 50 volts. And there's twice as many turns on the secondary as there is on the primary. So across here, you end up with 100 volts. Now, it'd be nice if you got something for nothing or more than, but if you've got 100 volts to keep this 50 watts true, in other words, you're not getting anything for nothing, you've only got a half amp. Sorry, people. You end up with half an amp. Now, you've got 100 volts at half an amp. P equals E by I is 50 watts. Now, this load impedance, what's that then? Given that calculation. R equals E on I, 100 over a half is 200. So that's just confirming that your load will end up 200 ohms. So it's just an explanation for people that may not be familiar with it. That's the bit I forgot to put into the figures. Now, all right, so what sort of resistance have we got to put as a load, or sorry, reactance for a load of 200 ohms? What sort of reactance would you suggest that we work with? Gave you a rough figure. 5 to 10 times. So this reactance has got to be 5 to 10 times 200 ohms. So in other words, the reactance has got to be something like 1,000 ohms. Now, if you go back to the reactance chart and look at that, you've got, say, 1,000 ohms, and we know what frequency, what frequency do you do this calculation at? Is it the top end of the band or the bottom end of the band? Yeah, bottom end. It's all starting to click. It's starting to come good. So, in other words, 80 metres, 160 metres, you work out 3.5 meg or whatever, 80 metres, and you say, right, for 3.5 meg, I want a reactance that'll give me 1,000 ohms. So you look up the chart, the reactance chart, and that'll say, oh, maybe 20 or 30 millihenries inductance. Now, given that, you then use this AL figure and go backwards in your formula. L equals N squared AL, therefore N equals the square root of, yeah, whatever. Or you just, you know what the AL is for one term, and you know you after, well, I'll do it easy, 40 millihenries, and the AL is, in other words, do this example back there, the front, you know that every time you double the turns, you're going to get 4 times the reactance. Or 4 times the inductance, sorry, which is 4 times reactance, same difference. And therefore you know what the number of turns are required on this transformer. So it's as simple as that, actually. That's basically what it's all about. Any queries? No? It's all, you can all rush out and make a transformer.
So that's a balun there.
That's a balun. It's a very...
So as soon as that comes, I ask a stupid question. One end of that is obviously balanced and one end isn't.
Yep.
How does the circuit diagram of that relate to that? Because that is always...
Oh, what
I've always tried to back work what I'm actually looking at.
Yeah, what I've done, and this is, it all gets down to a bit of experience, is you can put wire onto a transformer in many different ways. You can use Biflow winding, you can use scramble winding, you can use layer winding, you can use pi winding. Anybody familiar with pi? Sean won't know, he's too young. But RF chokes, remember when RF chokes used to just be air cord? They never used to have ferrite in them?
In pairs.
Yeah, in layers, there's sort of a squiggle layer. And the reason why they do that is to
Reduce the capacitance between the line.
in other words, they stack high and they scramble line. But given that we're talking about RF transformers in particular, the idea is to keep the number of turns down. Now, I think that example is about 20 turns. Now, what you can do is use Biflow wire, which is just 2 wires together, and you wind them on together. Now, this application, it just so happens the application I'm experimenting with or playing with, I want 200 ohms. And one of the things we didn't discuss is auto transformers. That's an auto transformer. In other words, the primary is also part of the secondary. So you get a lot more current in that winding there than you do in that winding there, 3 times more actually. Yeah. Sorry?
That's where I got confused.
Yeah. And what you do, if you use a Biflow winding, in other words, these 2 windings are wound simultaneously. They're both put onto around the ferrite at the same time. Then what you do is you get the 2 ends and you so that they're your 2 windings. You then virtually take yeah, that's right. So it means that with the application I've got, where you're driving a half-wave antenna, the antenna goes on the active side and the other side's ground. Now, I'm experimenting with it. I made up a half-wave for 2 meters many years ago, and it was quite successful. I was quite happy with it. And for somewhere I went through the books to try and find what the impedance is of an end-fed half-wave. Now, I'm quite sure I've seen in TAFE notes that it's 200 ohms. Now, it's funny because also the transformer I made many years ago was also 200 ohms. Now, where the danger is that you can get confused a little bit is that an antenna is a tuned circuit. It has an inductive and a capacitive element. And therefore, in theory, across the 2 ends of the antenna, a half wave is very high impedance. And therefore, you might think that you have to drive it with high impedance. But because the antenna actually radiates into atmosphere, it's as though it's got a resistive load on the antenna. In other words, it's absorbing energy. And if it absorbs energy, it can't be an infinite impedance. It's got to be a lot less. And given that a quarter wave ground plane is 75 ohms, I think it's right in an end-fed half wave is 200 ohms. But I'll find out the hard way. I've got a bit of a way of testing it. I've just put a bit of wire up on a squid pole on 10 metres and just see what happens. I'll measure the impedance using my little meter. Any queries? How we go? Now, general discussion.
I noticed in some antenna books, they reckon it's between 2,500 to 5,000 ohms. It's a grey area, isn't it? It depends upon the height above the ground and surroundings. And
all I could find was that it said that they were high impedance. Now, high impedance as compared with 50 ohms, I think 200 ohms you might consider for radio applications is high impedance. But don't forget, do you realise or understand what I'm saying about the fact that a half wave radiates? Yeah. So it's like a tuned circuit with a load on it. If you were to draw that, an equivalent circuit of an antenna, a half wave that was radiating, what you do is show a tuned circuit with a resistive load across it. And that's what your transmitter is driving, that resistive load.
Especially when you tap into it, it's got to fall, hasn't it? When you sort of tap into the end of it there, you're putting a load on there.
Yeah, well, you're coupling to it, and you're coupling to a radiator. And therefore, in theory, or I'm reasonably confident that it's true. And there is a significant advantage in running a half wave. You don't have a balun hanging in the middle of your 2 quarter wave sections and dragging it down, which isn't always convenient. You can, with the same balun and same setup, you can either run the aerial vertical or horizontal. Now, the only thing I don't know is behind the actual transformer, the earth side, as to how well it has to be earthed. The transmitter has to be earthed, whether you have to have an earth stake or whether the earth of the transmitter, etc., is adequate. So how we going, people? Time for a cuppa? You've all had enough. You're all starting to... Well, I hope that it's given you some food for thought anyway. And also, that was one thing I didn't cover, allow me to catch up, is one of the problems is with the transformer is magnetic toroids, being a closed magnetic circuit, and ferrite, they saturated 4 kilogauss. Now you go down to the low end of the band and you try and apply a reasonable amount of power, and you run the risk of saturating the transformer, because the back EMF E equals 4 KNF phi, and if that E goes up, then the phi goes up. Yeah, that's right. Something's got to change, and the only thing that can change it, because you don't change the turns or the waveform, then the flux density goes up, and you run the risk of it saturating the actual transformer. So one way of overcoming that, and Colin was alluding to it before, was to have an air gap in the circuit. Now that, in other words, air doesn't saturate very easily. So with an air gap, you can run up much higher in flux density.
I've got one question on it.
Yeah.
I noticed on your diagram up there, it seems to indicate that the phasing of the primary and secondary are opposite. You've got turns going one way, then turns going the other. How important is the phasing of the primary and secondary windings? Because if the secondary winding is isolated and reversed, it's still tied to ground, but the distributed capacitances and things like that between the 2 windings will change.
Yeah, your point's good. In other words, you've got to take the taps off when you run a Biflow winding, you've got to you end up with around the core, you end up with wires like that. And what you do is, that's Biflow now. I'll show that by putting in a different colour. So what you do is you take the end of one winding and hook it through to the other. Now, if you do it, if you just short it there, then it's actually back the wrong way. The current going through that is then going back the other way, and you don't end up with any resultant flux. So what you do, you take it through, you take it from the green one to the blue one, and then you take the actual winding out like that. Now, the whole advantage of Biflow winding, especially in this application, is that between these 2 windings, which is these 2 windings, what are you getting there? Capacitance. So in other words, you're getting 2 lots of advantage. You're getting the inductive coupling, plus to some degree, you're making that capacitance in your favour. You're using it. So that answers that. One thing that I was sort of sneaking up on is that transformer has got a hell of an air gap. All it is just ferrites from a transistor radio. Now, remember I said one of the problems you end up with is that you end up with too much inductance and virtually 1 or 2 turns. Now, it just so happens that transistor radios have a lot of turns, but at about 1.5 meg. We want to run up at about 5 meg, and we want less turns, which E equals 4K NF5 works very well. Now, one of the ways of stopping the transformer from saturating is with an air gap. So in other words, this is a possibility readily available. You can go down the street and buy old ferrite rods, or you might be able to recover them from radios, and they're worth a bit of an experiment to see what you can make up from them. The other thing is when you do finish the transformer, you've got to then work out what the power rating is. Now this one here, at this stage, the only value I've got or idea of power rating is comparing it with the commercial transmitter. I looked at the amount of ferrite and said, oh, that's probably 50% of the ferrite that's in the commercial set, so therefore it'll handle about half the power. But other than that, I've got to do some tests, which are ongoing, and the way I would test it is to hook it up to a dummy load, which in this case is 200 ohms, and then using the variable output power of the transmitter, go 5 watts, 10 watts, 15 watts, and check for third harmonic. Now, a sine wave, when you chop the top of it, approaches that of a square wave. In other words, the harmonics go up. The odd harmonics go up. If it was a triangular wave, in other words, a sine wave going into an amplifier that can't handle the frequency, it tends to turn the signal into a triangle. And then you get second harmonics. So what I would do is just hook this onto a transmitter, slowly crank the power up bit by bit, and just monitor for harmonics of that frequency. All right, how are we going? We're all saturated now? All right, thanks, people.
I think we've been all transformed.
Yeah, hopefully.
Any other questions for Ron?
You're all looking dazed and confused.
There were some really interesting questions there and really interesting discussions. So, all right, a big hand for Ron. Thanks very much, Ron, for your amazing presentation. One of the things about being involved in a radio club is that, particularly in BAREC, we're lucky enough to have members with this wealth of information that can share it with other members. And it really is quite an advantage to be involved in a radio club. I find anyway. Speaking of that, if anybody would like to do a presentation, you don't have to be a member of BAREC. Email myself at media@barec.net.au and provide some details of what the presentation is you'd like to do, and we can make arrangements. That would be fantastic. Another thing I'd like to mention is that we've been quite busy actually this year. We're doing training and assessments. And doing assessments for radio licenses. And it's really good to hear the candidates that have got their licenses come up on the nets. Our 2 main nets are on Tuesday evening, VK3AAN CV repeater, 147.150 on Mount Alexander at 8 p.m. And also a HF net on Thursday evenings at 8 p.m, 3.655. So join us on our nets if you can, and we'd love to hear you participate. With that, thanks very much for coming, and thanks to our YouTube viewers. It's been fantastic having you aboard as well. And thanks to Craig for the technology work, and also Cole for the video work, and Ron for doing the presentation, and everybody for coming this evening. Thanks very much. We'll see you all next time, and supper is now in the kitchen. Thank you.
Cover.